Welcome to CMC Microsystems webinar series. This is Jeet Narsingani, Systems Engineer at CMC. Today's talk is on SDR Development Systems. Before we proceed, I just wanted to highlight some few housekeeping tips. Right now, your phone lines have been muted to eliminate any background noise. We'll keep the questions towards the end of the webinar. If you encounter any technical issues, please send your request through the chat window, or you can email Krista at stevenson@cmc.ca. Today, we'll quickly give an overview of CMC Microsystems, followed by a webinar from John Yee. He's the Applications Engineering Manager at BE Cube. He will be talking more about the advanced design techniques using the miniBEE SDR platform. Following that, we'll have some time for question and answers. CMC Microsystems allows its clients to benefit from its national design network by getting access to leading-edge tools, technologies, and solutions, thus enabling research excellence. It also provides opportunities for networking, partnerships, and collaborations with fellow researchers, further enabling commercial success. So far, we have been supporting around 950 faculty at around 54 universities and colleges, over 3,000 graduate students and 3,500 undergrad students, and their collaborators, including 600 companies. CMC subscription allows you to optimize your research time by connecting you with information, tools, services, and price discounts. Also allows participating in Microsystems technology roadmap and proposal development. You can find more details about various subscription levels at the link mentioned there, cmc.ca/subscription. We provide over 35 different kind of tools which enable you from simulating a design to manufacturing and test. Just to recap, the software-defined radio Generation 1 platform, which is presently installed at various institutes, about 26 Generation 1 reconfigurable SDR platforms were delivered into 17 institutes. The platform constitutes miniBEE systems from BE Cube with the RF front-end FMC 111 card. It contains a Xilinx Vertex 6 chipset. The system allows for 2x2 MIMO configuration spanning from 400 MHz to 6 GHz. Please note that these systems are shared access, that is, they are available for no charge but require at least designer level subscription. You can find more information about the location of these systems and development system coordinators at the link mentioned here, and we will be sharing this information offline as well, so you can get all those links from there. CMC also runs a program called CMC Solutions. It's a collaborative cost-sharing program that leads to joint R&D projects. Recipients have to be from universities and or have industrial partners, which give them financial and human resources such as engineering support, engineering time, and any other costs related to hardware or software. The projects need to be in the area of micro-nano technologies or integrated microsystems, leading to some commercialization component. More information about the CMC solutions can be found on cmc.ca/CMC solutions. You can view present projects which are in progress, some of the technology themes which you can benefit from, and also get information on the application and some more FAQs answered there. Finally, I would like to highlight the community website. We encourage you to participate in the discussions on the community page. This page also contains updates, software updates, installation guides, and troubleshooting information. If you have any questions, we would love to hear back from you on the existing products and or any other new themes you want us to look into. So please let us know, and the information is available on community.cmc.ca. Before I hand it over to John, just keep in mind that we'll leave the questions and feedback towards the end of the webinar. Presently, your phone line is muted. We can't hear you. Just to avoid the background noise. If you have a question and want to speak up, press *7, that unmutes your system. And to mute it, you can either press the mute button on your system or *6. You can also send your questions using the chat box found in the WebEx website. So without further delay, I'll hand it over to John, and he'll take it from here.
Okay, good afternoon. Can everybody hear me now? I think I'm already unmuted.
Yes, we can hear you.
We can hear you.
Okay. All right. Thanks, Jeet, and thanks, Krista, thanks CMC for organizing this webinar. And I also want to thank everybody who participates in the seminar who are obviously interested in our miniBEE SDR platform. So my name is Jiang Ye, and I work in the BQ Application Engineering department. So let me start with today's seminar. Is how to design we are going to cover some of the advanced design topics for miniBEE. So the agenda for today's seminar is going to be organized as these following parts. First, I want to do a quick review of the miniBEE SDR architecture. My assumption is most of the attendees are already having some experience with the miniBEE SDR platform, and then I will discuss in details about the clock generation of the miniBEE SDR analog frontend, which from the feedback I got from CMC, there are quite a few questions regarding how the reference clocks are generated on miniBEE SDR platform, which is also an important topic for any communication system design. And in order to understand the clock reference design, there are drivers that we use to program the chips to generate the different clocks. So I'm going to cover, go into the in-depth of the drivers as well. And lastly, I will answer some questions when time permits. So this is a overview of a diagram of how a miniBEE SDR-based application is designed. So as you can see, the miniBEE SDR platform is consists of a general-purpose processor, which is the quad-core Intel i7 module implemented in the B7. Implementing the miniBEE, where you can do where users can run simulation verification and first post processing as well. And in the center of this diagram is the Xilinx Vertex 6 FPGA, which are users can program the FPGA to implement the real-time processing algorithm. And to the right of this diagram is the mixed signal card, which is the FMC 111. It consists of ADC, DAC, and RF front-end. So in terms of software, the embedded software is executed on the FPGA, which we implement a microBlaze soft processor on the FPGA, which I'll go into some of the details in terms when we talk about the drivers. And on the GPP, we have the BQ has also implemented some firmware which allows users to program the FPGA and using Minicom to control and configure what's going on inside the FPGA, in addition to what we call a daemon, B4D, which allows users to remotely communicate with miniBEE or with the FPGA from a remote host in the same network.
Sorry, John, just a quick note. Do you want to zoom? Do you want to maximize your screen? Because I'm seeing two pages there.
Oh, I see. So I think I need to swap the display. That's what it is.
Okay.
Yep, I'm sorry. So
No problem.
I was looking at my large display, but okay, I think this is the screen you see now. Okay. Is it good now?
Yeah, it's good. Thanks.
Okay, all right, yeah. Sorry about that. So the SDR platform is essentially a mini plus FMC 111, and the FMC board is introduced in 2013. As G already covered, it has a 2x2 MIMO configuration. And we also provide the BPX driver that allows user to initialize it to a default configuration. And we also those drivers are also I guess open. It's not anything hidden from the users. If you want to take a look at it and change it, it's all there. I will show you where those drivers are in the later time of the webinar. So I'm going to quickly cover. I want to bring up this diagram to show how the receiver is implemented on FMC 111. So the receiver architecture implemented on FMC 111 is a direct conversion receiver architecture. So if you look at a direct conversion receiver, so it has from the antenna, it will go get into a band select filter before it will gets amplified through a low noise amplifier, and then a pair of a mixer which generates quadrature LO signals will transform the signal from RF frequency to baseband frequency, and then before the ADC is used to convert the signal from analog domain to digital domain. We have a pair of low pass filters to select the proper baseband signals. So therefore, if you look at the FMC 111 block diagram, you can see on the receive side we have two RX paths. So if you look at this diagram, consists of two symmetrical paths, both TX and RX. On the top of the diagram is the TX path. On the bottom of the diagram is the RX path. So on the RX path, you can see that when the signal comes into from the SMA connector, it can go either enter from a cable or from an antenna. So we have implemented a market specific filters to that can be selected according to the frequency band that your application is target. And then these two stages, low noise amplifier will perform the LNA functionality in the direct conversion receiver. And this stage, and this is the ADI demodulator chip, which performs the transformation, the functionality of transforming your signal from RF band to baseband. So before it gets into the FPGA, that's where your digital signal processing will take place. The analog signals will be digitized by a pair of analog to digital converters that performs the digitization of I channel, in-phase channel, and quadrature channel, respectively. So at the center, today what we are going to cover more in detail is how the clock reference is generated. So that's part of subsystem are located in the center of this diagram. The central component, which is the LMK PLL chip from Texas Instruments. So, and then from here you can see there is one FPGA reference clock being generated from this PLL chip. So this is the FPGA reference clock. So how is reference clock used in a typical FPGA design that's targeting a miniBEE application? And so when you bring up a reference, bring up our reference design. So when you double click, we have a platform configuration block. Here is, this dialog gives you the option where you want to enter the reference clock and your user IP clock frequency. So, So look at this diagram. The reference clock specifies this. So this is FMC reference clock from FMC 111, and it goes into the FPGA and an MMCM, which stands for Mixed Mode Clock Manager. This MMCM is the clock generator inside the FPGA. So this MMCM will further synthesize a user IP clock, which can be the same in our reference design. It is the same frequency as the reference clock rate. Well, in other cases, if you choose to implement your user IP at a different clock rate, which it is also feasible to generate a user IP clock at a different clock frequency. So this is how these two clocks are mapped into an FPGA application design. So this reference clock is representing the FPGA reference clock coming from the FMC 111 to the Vertex 6 FPGA. Well, the user IP clock is the clock that's generated, based on the FPGA reference clock. So this diagram shows the overall clocking diagram of, you consider not only consider the FPGA baseband, clocking, but also the global, all the reference clocks on the RF, on the mixed signal board, which is the FMC 111. So the PLL chip, which is the LMK0408, it should be 0408. This chip, actually, you can look up from the TI website if you want to know more information about this PLL chip. This chip is provided with the input reference. It needs a reference. By default, we are using a 6144 MHz VCXO as an external clock input for this PLL chip. Based on this reference clock, it will further generate different clocks, such as the two DAC clocks for the two TX paths and the two ADC clocks for the two receive paths. In addition, it will also generate a synthesizer reference clock. By default, is 30.72 MHz to these two synthesizer chips that generates the arrow signals for both the TX signal path and the RX signal path. And then last but not the least, it will provide the FPGA reference clock to the Vertex 6 FPGA, where your baseband processing will be used this as the clock reference. So if you look, so another path. So this is one of the reference clock input for this PLL chip, which is our default configuration using the 6144 MHz onboard crystal or VCXO. Another reference clock input can be coming from the clock input SMA connector. So this is another option. You can configure configure using our firmware to configure the PLL chip to take, instead of using the 6144 megahertz crystal as reference clock input, you can set that to use this clock input as reference clock input. With this feature, you can synchronize the global reference of your FMC 111 or your SDR application with an external clock source, or you have multiple equipment or multiple miniBEEs. You can use this clock input to synchronize to have a common clock reference across different miniBEEs. So there is also another SMA connector here, which you can enable the output a clock from this PLL chip. So if you want to synchronize more than one miniBEE, you can actually generate a clock and enable the output from this output sync clock SMA and connect this SMA to another miniBEE. So the other miniBEE or the slave miniBEE will be generating its reference clock, a global reference based on the SMA output from the master miniBEE. So this diagram shows the overall clocking diagram. So as you can see, because we have two DACs and two ADCs, they all interface with this FPGA. However, the FMC 111 only provides one FPGA reference clock to the FPGA. So our FMC 111 interface IP is actually assuming certain frequency relationship between the DAC clock and the ADC clock and FPGA reference clock. This is what I'm going to cover with this slide. So what's the default clock frequency implement on our reference design? So when you, for example, when you implement any design, you're using our FMC 111 interface IP, you want to know what exactly is going on after you load the FPGA. So our, that's how our initialization routine is going to execute based on these configurations. We will set ADC clock to 240.76 megahertz. So as you recall that when I call out the platform configuration with the two clock inputs, no, not two clock inputs, two clock specifications. One of them is the reference clock, the other is user IP clock. I specify 250 megahertz. That's just a close enough approximation of this 245.76 megahertz. That's the exact frequency that we are using on our FMC 111 based miniBEE SDR design. So the ADC clock is 245.76 megahertz, and the DAC clock is 491.52 megahertz, which is twice the ADC clock. So the DAC is configured to run with the 2x interpolation. So what that means is on both the TX side and on the RX side, the data rates are the same. The data rate being sent on the transmit side is still 245.76 megahertz. However, because the DAC is default to be running with a 2x interpolation, so the conversion rate for the digital to analog converter is actually 491 megahertz. However, on the ADC side, there is no change. So it's the input is 245.76 megahertz, and the FPGA reference clock is also running at 245.76 megahertz, so which is equal 1x the ADC clock rate. So the synthesizer reference input is 30.72 megahertz. So then, therefore, when you generate a local oscillator frequency for either the TX or the RX, there is a resolution of 30.72 megahertz. So you can generate a a local oscillator RF center frequency, which is n times 30.72 megahertz. That's the limitation for the where you want to place your RF signal at. So all these configurations are implemented through the initialization routine that's running on the FPGA. So how do you calculate the baseband rate from all these clock rate? So basically, what you can do is, okay, you have a user IP clock frequency, which is equivalent to, for example, the DAC, the ADC clock rate, or the data rate that actually on the TX path, the data being presented from the FPGA to the digital to analog converter is actually still the 245.76 megahertz, although there is an internal 2x interpolation in the DAC. So if I'm taking a look at the baseband design in the reference, the SDR reference design. So there is a 8x aggregate 8x interpolation implemented in the TX baseband signal processing chain. So that means our single rate is 245 megahertz divided by 8, which is 30.72 megahertz. In these the filters, 3 stages of filters, the first stage, square root raised cosine filter, has a roll-off factor of 0.5. So therefore, we can calculate the bandwidth of our TX signal spectrum to be using this formula. So this your single rate multiplied by 1 plus your roll-off factor, which is equivalent to about 46 megahertz. That's how wide your signal, the RF signal spectrum will be. So this is a spectrum analyzer screenshot after we program the bit file into the FPGA and then the application running. So you can see that we are running at the span is 300 megahertz. So each division in the frequency domain is about 30 megahertz. So this the spectrum, the channel of our generated transmit signal is about 46 megahertz. It's less than less than 60 megahertz, but more than 40 megahertz. So that's matching our system design expectation. So the natural question is, how do you want to change the baseband symbol rate? There are at least 2 options you can use to change the baseband symbol rate. For example, what you can do is you can keep, if you are not an FPGA, very keen on the FPGA design, you want to keep your everything the same as reference design. You don't want to reconfigure the clocks at all. So one thing you can do is you can keep the 245.76 megahertz ADC clock rate or FPGA reference clock rate as the same. However, you can change the interpolation ratio. The best design approach to do that is to use Xilinx multi-rate filter design toolbox, not toolbox, the system generator blocks from their Xilinx system generator tools. There are you can if you have those tools, make sure you want to use that. And system generator user guide from Xilinx provides a very good resource. You can look at their design. That's how our reference design is created. And so the limitation from that is your symbol rate is going to be 245.76 divided by n megahertz, right? So assuming you are running an integer interpolation, so you can have, in my design, reference design, we always have an integer rate change. So it's 2 times 2 times 2. So the aggregate interpolation ratio rate change is 8x. So you can also introduce, for example, 3x, 5x interpolation ratio into this transmit signal processing to change your rate. In addition, there are techniques from the system generator user guide. You can do a fractional rate change. So that means you can upsample by m and then downsample by n. So that you can play. You can tune a lot of knobs to change your baseband symbol rate. So another option is you can keep the 8x interpolation ratio as if you don't want to touch the reference design. However, you can generate different ADC and DAC clock frequencies. In order to do that, you will need to use SMA input as the reference clock for PLL. Recall that by default, we're using the 6144 MHz as our PLL reference clock input. So that's where the 245.76 MHz is generated. However, for example, if you configure the FMC 111, the PLL chip to use an external SMA input as ref clock, you can arbitrarily change that clock frequency and then generate a different ADC clock. Then your FPGA clock will be 1x your ADC clock. For example, if your ADC clock is 200 megahertz, then your FPGA clock reference clock is 200 megahertz. Then you can actually your symbol rate instead of being 240.76 megahertz divided by n, it will be a change to 200 megahertz divided by n. However, if you want to use FMC 111 interface IP provided by DCube, including a BPS software, a BPS design tool, it's still required to maintain the clock frequency relationship, meaning your FPGA design clock should be the same as your ADC sampling frequency, and your DAC sampling frequency is actually 2x of those two clock frequency or sampling rate. So that's the limitation you will have to follow in order to use our FMC 111 interface IP. So how do we configure the clock references? One of the, we provide in our BPS drivers these functions to, you can change the PLL reference source and its frequency. So, for example, the FMC 111 set global reference function, you can actually change this global reference between the onboard oscillator and the SMA, and then you can give it an input frequency. Whether it's 50 megahertz or whatnot, you can actually specify what the input frequency is. In addition, you can use another command is FMC 111 set local reference grid, local ref. So this particular command allows you to change the clock or the sampling frequency of each individual component. So the DAC, ADC, and the local oscillator and the FPGA reference clock, they can all be changed independently from each other. However, bear in mind that I described that there is a limitation. The limitation comes from our FMC 111 interface IP. there is the one, the ADC clock needs to be equal to the FPGA clock, and DAC clock needs to run at 2x of that clock frequency. So that limitation actually comes from the FMC111 interface IP, not necessarily from the from this chip. So this chip can give you a lot more flexibility. However, to simplify the design, we choose to implement we choose those frequencies to simplify the interface between the FPGA and the DAC or the ADC. So as people who have already used the FMC111 or miniBEE SDR, you know that you can use B4D send command from MATLAB to change these frequencies. So if you don't want to do minicom, you can use a B4D send command from MATLAB to write a script to change those frequencies. So the next, I'm going to switch from my PowerPoint to a shell window that I open up in the miniBEE. So let me I'm quickly describing my setup. So my setup is I'm logging on to a server, and this server, and then I'm remotely logging to a miniBEE, which also runs Linux. So that makes my that's how we like to design the application from a server. While you then load the bit file onto copy the bit file to miniBEE, and you can program the miniBEE from there. Because when you run the MATLAB software, the API, you don't actually need a license. The license, the BPS license, is only required when you want to compile and generate the bit file. If you want to say remotely communicate with the FPGA located residing in the miniBEE, you don't actually really need the license to do that. So you can actually install the BPS software on another remote server. So once you build the application, you can actually remotely debug or communicate and control your FPGA from a remote host. So this is the so this shell is already open up in a miniBEE. So if I do minicom FPGA, it gives me this shell, and then in this is another window. I already pre-compiled a bin file. It's FMC111 TRX demo.bin. If I program the FMC bin file into it, so you can these are the initialization messages we print out during when the initialization routine is executed on the FPGA soft processor. So you can see that we did print out intentionally, so configuring the DAC for 2x interpolation and fine-tune some reference frequencies based on the reference clock, the global reference, and this is the initialization routine we implement in our BPS firmware. So going back to the So we will take a look at this the driver source code. So see how our FMC111 driver is written. So we'll quickly look at this as well. So another question I got, because I want to go through those the discussion on the drivers, so I want to cover this slide as well. So this, some of the initialization routine executed on the microblaze processor is automatically run when you, of course, when you program the FPGA, and or you run MB for control -R to reset FPGA, in that. So these reset signal are generated to not as a hardware reset. We actually generate a software reset, if you will, to reset. It's like you have a PC, you try to reboot it, so it will go through the initialization routine that's executed on the microblaze soft processor. So that's the reset routine that's going to be executed when you initialize the FPGA. If you want to implement a hardware reset, for example, you have some registers or some FIFOs that needs to be reset. Well, our recommendation is to you can implement a software register, has for example, one of the bit as the reset bit for example, if you have a reset high mechanism, you can use that bit to drive all your blocks that requires so-called hardware reset. So after you run this initialization routine in your minicom, you can write the reset bit high and de-assert it low. So using that mechanism, you can reset the remaining logic that's implemented in your application. So with that, I'm going to say to look at the initialization routine. So that's part of the routine. You have to run minicom somehow interactively initialize your FPGA application. However, if you want to use for example, add on to the initialization routine of the BQ provided initialization software, what you need to follow some special coding style so that your own initialization routine can be included. So let's take a look at this, the drivers of our SDR initialization source code. So we are going back to the VNC window. So for those who have experience with this, you are aware of the output directory structure that's generated by the BPS tool. So go to the XPS base package and go to the drivers. So all these codes are generated and from our BPS tool, and they are visible by users. You can take a look at these code. You want to modify it, or you can learn from it to see how our FP software is written. It's all there. There is no nothing hidden from the users. So this is the SDR init. So everything under if for example, a function is defined in your source code, and below this, where the declaration of the function, if you put a comment as an init here, so this SDR init is going to be recognized as a part of the initialization routine to be executed in once your FPGA is reset, or upon programming of your FPGA. So that's part of your initialization routine. Essentially, if you look at this code, it's it's basically calling an XSDR init routine. That's another driver. So this is a BPS level driver that we encourage users to take a look at those. And if you want to add on some functionality, that's okay. And the XSDR init is the EDK level software. So that's something we don't, it's also there, but it contains a lot of low-level drivers. But in any case, I'm going to take a look. In this presentation, I'm going to show you some of the routines there as well. So for example, if I want to add my own initialization routine, how? So if you want to add your own initialization routine, what you can do is to, in the source subdirectory of the project folder, you can actually add your own routine right there. So for example, I'm just creating a very simple initialization routine. It does nothing but print out my FPGA application initialization. So you need to follow the same coding style. You declare my init and put a comment, /star init, and end it with a // Tell our BPS tool this is the user initialization routine. So this routine will be later on included in the main.c generated by our tool. So if you look at this tool, so this is the main.c. So this is the main program executed when the FPGA is programmed. So of course it has to this is our software. We actually added some tiny shell commands. Those commands are available. Those are the minicom commands made available to our user. And that's from here, at initialization routine, you can see here we call init I2C, init SDR, which I just showed, and then it also included my init, which does nothing but just print out the message. That's where my initialization routine is going to take place. So with that, I'm going to show you here. So I already pre-compiled the bin file here, which is FMC111 TRX demo2.bin. And then, so after, you can see that, that's where, my FPGA application initialization message displays. I mean, this is just gives you a quick example how you can initialize, include your own initialization code when you build an application targeting miniBEE SDR. So when you type ? You can see it before when I show you the main.c, there are a lot of commands, tiny shell add commands. Those are the nectar.os or minicom commands that's provided to the user. So these are the commands, FMC111, etc. For example, LED toggle, FMC111 get status. So ADC1LO is not locked for some reason. So in any case, these are the commands that we provide through the minicom commands. Those actually in main.c, you can see how those commands are actually added. If you desire, you can actually introduce your own commands. So we have in our BPS user guide, there is a section about how to introduce your introduce the user-defined commands as well. So with that, I'm going to go back to the presentation again. So there are we showed you the initialization routine. Oops. Why is it not showing? Okay. So the initialization routine I show you are our BPS drivers. So there, because due to the time limitation here, I'm going to quickly point you to this. In the base package, we also provide the drivers for the EDK drivers. So how those initialization routines are implemented are all based on the EDK drivers. We also included in the base package, where you can also the users are also welcome to actually see the source code. It contains a lot of low-level drivers, such as I2C transaction, SPI transaction, etc. So actually, quickly, I'm going to just you can see that miniBEE has multiple chipsets in the signal chain. I want to bring your attention to a new product. I mean, a nanoBEE. So BCube, our company, our engineers need to write drivers for just a lot of drivers, but for limited operation modes, because all these chips are have a lot of operation modes. So we actually have a new product called nanoBEE. It's just one integrated SDR transceiver chip. It's from ADI 9361. So ADI provides the software driver. So think of it as the EDK driver has already been written by ADI. They write tens of thousands of lines of code, and they cover most of the modes that their SDR transceiver chip is going to operate on. So we only need to develop high-level APIs to abstract the low-level details. So that way, actually, we can cover a lot of modes that definitely increase the flexibility of the SDR application. So, and this, we actually have a nanoBEE demo showed on GlobalCom 2014 last year in Austin, Texas. So this one in particular is we had a pair of nanoBEEs. One of them acts as an LTE transmitter, transmitting LTE waveform, while the other is receiving LTE receiver. And we use the toolbox provided by MATLAB to do the baseband processing on the host laptop. So we are capturing the RF waveform and display the spectrum. Then this window shows because of the toolbox, the powerful toolbox, we can do channel estimation and plot the constellation of the decoded signal as well. So with that, that's going to conclude my webinar today. So of course, finally, I want to thank CMC for organizing this webinar, and I'm going to take questions if there is any. If there are more, because of the time limitation, there are more questions, you can contact CMC or send the email directly to support@bcube.com. But you're mostly encouraged to contact CMC first.
Thanks, John. Thanks very much. That was very interesting. Folks on the phone, if you have any question, please press *7 to unmute, and please let us know if you have any. Looks like there are no questions, so Maybe I'll ask one question, John. You mentioned about the local oscillator, right, connecting the two channels, transmit or receive in the FMC 111 card.
Mm-hmm.
I was just wondering, is it possible to control those two channels at two different frequencies? Is there a way to control the local oscillator separately for each channel?
Yes, I mean there is a command called FMC set local frequency, set LO frequency. You can, so that gives you, if you type that minicom command, it will give you a prompt. Actually, give you the format of the command. You can specify whether you want to set the channel A's local frequency or channel B local frequency, so they can be set independently from each other.
Okay, thanks. We still have a few minutes. Any questions? Please press *7 to unmute. And okay, looks like we have no more questions. As mentioned before, if you have further questions later on, please let us know, and we can try to answer those questions with help of BE Cube. Once again, thanks for joining this webinar, and we will post this webinar online, and we'll send out the link once it's online. Thanks again, and have a good day.
Well, thank you. Bye-bye.
Bye.